Alright, hi, I'm Nikki Kim, and for my physics final, I'll be teaching you guys about simple harmonic motion in a really broad overview. And this is a motion in physics. It's periodic, which means that it repeats and it's cyclical. So it's the period of this motion is how long it takes for one revolution, one finishing of the cycle. And periodic simple harmonic motion is also dictated by a restoring force, which is the force that will bring back an object once it's removed from its equilibrium point. And I mean, as you can see, this is a motion that's usually attributed to springs and pendulums and things that would move in a manner like that. And you can see this in the pendulum. Sorry, Lauren, we're coming this way. This is a simple pendulum of mass m and length L. And if I move, like, this is its equilibrium point. Right now it's at rest, it's not moving. If I displace it from its equilibrium point from here to here, and I let it go, that's not very good. But the restoring force on it is the gravitational force. So the only thing acting on it is gravity. And that's the restoring force. It's trying to get back to equilibrium, but as you can see, it swings through, which means that it's got too much energy and it swings right past its equilibrium point, and then gradually reduces and will eventually get back to hanging still. That's a really crappy pendulum. Another version of simple harmonic motion can be a mass and spring system, like a cart like this. If I attach a cart to two springs, each with a certain spring, what's it called? Certain spring constant. So they'll be displaced and they'll bend and stretch a certain distance per coil or whatever. And if I remove this from its equilibrium point again, right now it's stable, it's steady. If I move it to here, there it goes. It'll go past and through the equilibrium point. And then continue. And because this is not frictionless, it'll eventually slow down just like the pendulum did. And you can further analyze this motion in a chart like this. So if you use this, because it's like a linear example, right now we have the cart equilibrium position. It's distance 0, I guess. When I moved it, I moved it at an amplitude A. The amplitude is the distance away that the cart or the pendulum will move from its steady position. So amplitude, and then I moved it from here to here, and let the cart go, and it moved through the equilibrium point to amplitude on the other side. So it went to a negative amplitude. And these two are equal, and when I released it, I increased its potential, when I pulled it back, I increased its potential energy, and then when I released it, that potential energy turned into kinetic energy. So let's see on the side of the chart here. Pull it back to here. Kinetic energy is at a minimum because there's no velocity. Let it go. When it reaches the equilibrium point, the kinetic energy is at a max because it's moving at the fastest velocity possible. So kinetic energy is a maximum in the middle, and the velocity is a maximum in the middle, which means that it's also at a minimum at the two amplitudes. And also, if you look at it that way, the other kind of energy I could have is potential energy. And the potential energy of any simple harmonic motion device, whether it be the cart or the pendulum, is always at a maximum when I displace it from the equilibrium. The farther I go, the farther I stretch the spring, and the farther I remove the pendulum from its middle point, that's the more potential energy I have. And then I let it go, and potential energy is turned to kinetic energy. And because of that, the acceleration at the amplitudes is at a maximum, and the acceleration at the equilibrium point is at a minimum. And I think I'm done. Right,
wait, we need to wait 5 more seconds.
Oh god, that's simple harmonic motion. It's pretty simple to explain it. Well,